Okay, so this kind of introduces us to Chapter 7. And what our kind of topic is going to be for the next couple days is called Ionic Naming. Okay, we're going to name compounds that are ionic. Okay, and I'm going to tell you kind of in general terms what an ionic compound is. We're going to really dive into what compounds look like, how they bond, all that kind of stuff next semester. But in general, an ionic bond, okay, or an ionic compound is between a metal and a nonmetal. Okay, so on the periodic table, where are the metals located? On your periodic table, where are metals located at? On the left side, the right side, middle, top, bottom, what do you think? Okay, middle and to the left. They're to the left of that stair step. Okay, so on that stair step are kind of the metalloids. So everything to the left of that is metals. So a far majority of your elements on the periodic table are metals. Like a vast majority of elements on the periodic table are metals. Okay? The nonmetals are things on the right side of the stair step. So if you look at the periodic table in class, things to the right of that red stair step line are nonmetals. Things to the left of it are metals. There's a few metalloids kind of found in the middle there. We won't deal with those quite as much, but for the most part, we have metals on the left side and nonmetals on the right. So when you form an ionic compound, or we look at these ionic naming, we're going to have an element from the left side of the periodic table and an element from the right side of the periodic table. Also, another way to think about an ionic compound is that it's between not only a metal and a nonmetal, but it's between a cation and an anion. Okay, does anyone remember what a cation is? A positively charged ion, and an anion is a negatively charged anion. A negatively charged ion. Okay? So we're going to look at, I'm going to give you a periodic table that has the charge of every element that helps you put together these compounds. But essentially what we're looking at is when we have an ionic compound, we're taking a positively charged atom and we're pairing it with a negatively charged atom. Okay? Or we're taking a metal and we're pairing it with a nonmetal. Okay, so that's the general overview for ionic naming. So taking a look at our periodic table of ions, I want you to look at the group 1 elements. The group 1 elements, what do they all have a charge of? +1, right? A positive, right? So a positive, anytime we see a charge given without a number there, we assume it's a 1. Right? So if it's a 1, you can leave that off. You're more than welcome to write it also. Okay, so we see a positive. So all of the group 1 elements have a +1 charge. So let's think about how that charge was determined. Okay? So reviewing back to our valence electrons, do you remember what valence electrons are? The outermost electrons. So all of the group 1 elements have how many valence electrons? All of group 1 has how many valence electrons? 1, right? They have 1. Okay, so if I'm hydrogen, here I am, I've got my 1 valence electron. Okay? Do you think it's going to be easier for me to gather 7 electrons to fill my octet or to give away my 1 extra electron? Give it away. So if my electron goes bye-bye, what does that leave me with? What type of a charge? A +1. Right? So that's where these charges come from. It's talking about what most commonly happens with their electrons. So lithium works the same way, right? Lithium has an extra or a 1 valence electron, and so it wants to give it away, and most of the time it's going to give it away, which would leave it with a +1 charge. Okay, so that's where those charges come from. Same thing goes with the group 2 elements, like beryllium, magnesium, calcium. Is it easier to take in 6 electrons or to give away 2? Give away 2, which is why those elements all have a +2 charge. Like other elements, like that's when they would bond, right? They're giving them to that other element. Okay? And calcium's like more comfortable hanging out with that +2 charge, so it can bond with lots of other things. So they're just kind of letting them go. Okay? Now let's jump over past the transition elements. The transition metals don't follow the same types of rules, okay? So let's jump over to group like 18. Do any of those elements have a charge? No, why not? Full octet, right? They have 8 valence electrons. They have a full octet. So group 17, how many valence electrons do they have? Fluorine has usually how many? 1, 2, 3, 4, 5, 6, 7. Usually has 7. And does it want to take one or give one away to be happy? It wants to take one. So here's its extra electron. So if it's got an extra electron, what's that make its charge at? -1. An extra electron would give it a negative charge. Right? That's tricky. Extra electron would be more negative. Okay, so I'm just kind of giving you a background as to where those charges come from. That's not super important for us understanding our naming at this point, but I want you to understand these charges aren't arbitrary, right? It comes from the way their electrons behave. Okay, does that kind of make sense? The ones in group 14, like carbon, silicon, germanium, they don't have anything listed. That's because it's just as easy to give away 4 as it is to take 4, right? They have 4 valence electrons, so it's easy to take and give, and so they can kind of be a +4 or a -4. Okay, boron kind of works the same way. Okay? Okay, so the first type of naming that we're going to deal with is called monatomic ions. And what do you think the word monatomic means? Good. Good. So these are single atom ions. Okay? And so this would say, if I wanted to name oxygen with a -2 charge, right, that's an anion, and it's only a single oxygen atom. So this would be considered a monatomic ion. Okay? So the way we name monatomic ions is really simple. Really simple. Okay? Anions, like oxygen, they just end, in IDE. That's it. Okay, they end in IDE. That's the only thing that changes. So if you look on your periodic table of ions, you'll see all of those negative charges. It's not oxygen anymore, it's oxide. And it's not sulfur anymore, it's sulfide. So do we see that on our periodic table of ions? Everything over here now ends with an IDE. So ending in IDE means that it's a single atom with a negative charge. Okay, do we see the difference there? So IDE means that it's got a charge that goes with it. Naming a monatomic cation, like Na+, cations just get to keep their name, so there's no changing involved there. So there's nothing that changes between sodium and sodium +1, right? You just have to say the charge for a cation. That's really it. Okay, so if I was trying to name this monatomic ion, I would just call it sodium +1, right? Or sodium. Okay. The name for this. Yeah, what do we think it is? Sulfide. Okay. Give me the formula. For phosphide. What's the chemical formula for phosphide? P -3, right? And it doesn't matter if you write it 3- or -3, right? I'll always write it -3. It doesn't make a difference. Okay, what if I ask you for the name of just this, Se? No charge. What happens if there's no charge? What would we call it? It's not an ion anymore. Yeah, this would just be selenium. Right? But the difference between selenium and selenide is that -2. Okay, so selenium is an anion, or it's a non-metal, but it doesn't have a charge, right? So that's why it gets to keep its regular name, because it doesn't have a charge. It's not an ion at this point. When it becomes Se-2, then that makes it selenide. Okay, so there's a little bit of a difference between those. Okay, positive ions will keep those the same name no matter what. Okay, any questions so far? Okay, the next thing we're going to look at is called polyatomic ions. Okay, more than one, good. It's an ion with multiple atoms. Okay, so on the table, on top of your periodic table of ions, there's some that I want you to maybe put a star by or underline or something that we'll use often, okay? The first one is carbonate, which is CO3 -2. Next one we'll use a lot is cyanide, Cn -1. Okay, can kind of skip over those hydrogens right there. Nitrate and nitrite, those are both in the middle column toward the bottom that we might use quite often. In the third row, phosphate is something we might use pretty often. And then down at the bottom under positive polyatomic ions, ammonium is one that we might use pretty often. Okay, there are additional, this is just some of the most common polyatomic ions, but these are ones that we might use often. Okay? So just something to keep in mind. And that's not something that I'm going to have you memorize at this point or anything, but polyatomic ions, you just need to understand those are multiples, and those never change names. So phosphate is always PO4 -3. Cyanide is always -1. Cyanide is always Cn -1, sorry. And we're going to be able to pair those polyatomic ions just like they were acting as our anion in a regular compound. Okay, so we'll be able to pair those with metals to form an ionic compound. Okay? Okay, now we're going to start into the real naming parts. So we started with kind of how things get their names, but now we're going to start dealing with putting together and naming binary compounds. So binary, what's that mean? What's that lead you to believe? How many are we dealing with? Yeah, we're dealing with 2. Sorry, my handwriting's not the best right there. Okay, binary compounds. These are compounds composed of 2 elements. Okay, so in a binary compound, we have 2 elements, and in any ionic compound, specifically, or including binary compounds, the compound must have an overall neutral charge. And I'll kind of talk about what that means a little bit more here in a little bit. Okay, and what does neutral charge mean? What's the numerical value of a neutral charge? 0. Okay, I'll write it up. Okay, so it needs to have a numerical charge of 0. And I'll show you how we work together to get that, but that's something that we need to keep in mind. Okay, so when we make these compounds, we're going to start putting them together in a way that they balance to end up as a 0 overall charge. Does that make sense? All right, so let's just start from the beginning. This chapter, we do a ton of examples, a ton of practice problems, because that's really the way that you can get the rules and the kind of rhythm of naming down. Okay, it's just a lot of practice. Okay, so let's start with binary compounds. So let's say that I want to make a compound between magnesium and bromide. Okay, I want to form a compound between magnesium and bromide. Okay? So first thing that I'm going to do is I'm just going to write out these elements and their charges. Okay? So magnesium is Mg, and what's magnesium's charge? +2. And I have bromide, which is Br. What's the charge for bromide? -1. Okay? So when we put a compound together, it's really important that the cation, okay, or the positively charged one, that element, that's the cation, it needs to go first in our compound all the time. Okay? So the cation has to go first. Okay, and if you're really not thinking in terms of cation and anion, what you need to think about is that your compound needs to come together from left to right on the periodic table. So which of these two elements is further left on the periodic table? Magnesium. Okay, so whichever comes first on the periodic table needs to come first in your compound as well. Okay, so work left to right on the periodic table. Okay, so I'm going to show you a couple different ways that we can put this together. If magnesium is a +2 charge and bromide is a -1, how many bromides do I need to balance this out? I need 2, right? If magnesium is +2 and bromine is a -1, I need 2 of those -1 charges to balance. Would you agree with that? MgBr2, right? That's how we would write it. We need 2 bromide atoms that each have a -1 charge to balance out that +2 charge. Okay, so let's just think about it and check ourselves here a little bit. Okay, bromine or bromide has a charge of -1, and we're saying we need 2 of them. Okay, which would give us on this side a charge of -2. Would we agree? On the right side of our compound, we have a -2 charge because we have 2 bromides, each of which have a -1 charge. Yes, are we on the same page so far? We have 1 magnesium atom because if there's not any subscript there, that means we think there's a 1 that has a +2 charge. +2 minus 2 gives us a total charge of 0, which is what we want. Okay. Let's try a combination now between potassium and phosphide. Potassium and phosphide. So the cation needs to come first, which is potassium. Its charge is +1. Phosphide's charge, phosphorus is just P, right? So phosphide has what charge? -3. Okay, so if I want this compound to balance, how many potassiums do I need? Right? Let's write it out like this. Right, maybe this will help a little bit. Oops. +1. So now I have 1, 2, 3 pluses. That gives me a +3, and I have a -3. Okay, so that means I would need to have K3P. Does that make more sense writing it out that way?
Yeah.
Okay.
So the goal is to get to 0.
The goal is to get your total overall charge to 0. That's right. Okay. Any other questions? All right, let's try a couple of these on your own real quick. So let's get a combination between chloride and barium. And then a combination between magnesium and oxide. Raise your hand if you agree. Yeah, that's what I had. Perfect, perfect. Okay, so why does barium have to come first? It's the positive. Barium has to come first because it's a positive. So if I'm putting these together, barium is +2, chloride is -1. So I need another of those chlorides to get me to be balanced. Right, so that leaves me with BaCl2. Okay, does writing it this way help you picture it a little bit better? Writing out the chlorines, like by themselves. Does that help a little bit? Okay, BaCl2, perfect. Okay, magnesium and oxide. Anyone have what's it called? An example? All right, Hannah, what do you think? MgO. Yeah, perfect. Perfect. Okay, they were a +2 and a -2. So they balanced perfectly already. There was no need to add any more of either element, right? They were +2, -2, so it works out. If there's a 1 there, we just leave it off. So just take it off altogether. Okay. It's not necessary to have Mg1 and O1. Yep.
Potassium and phosphate, why is it like K3P, not KP3?
Okay, on potassium phosphide, so let's go back. K3P, we needed just 3 of our potassium atoms, not 3 of our phosphide atoms. Right? Potassium was a +1 and phosphide was a -3. Okay, so to get this even, I need 3 of these potassium atoms, right? +1, +1, +1 gives me a total of +3. And I only need 1 of these atoms because it's a -3. Okay, does that make sense? So it's not like the second one always gets a subscript, right? That's not like a rule that we follow. Whatever one you need more than 1 of, that one needs to have a subscript. Okay? Okay, so now let's start looking at some that are a little bit more complicated where one of them is not a 1. Right? What happens if one of them is not a +1 or a -1? Okay? Let's look at a combination between aluminum and oxide. Aluminum and oxide. So aluminum is Al +3. And oxide is -2. So we can't have fractions of an element, right? We can't take parts. What's the least common multiple between 2 and 3? 6, right? We're going to have to get these charges to like a 6 somehow, right? Do you understand where we're going with this a little bit? Not quite, or... Okay, we can't balance a 3 with a 2, right? If I double the 2, that gives me now a +3 and a -4, right? So I have to kind of keep adding them until I can get to a charge that balances out. So that's why we did the least common multiple. That's what we were looking for. So if the least common multiple is 6, 2 aluminums would get me to a +6, and how many oxygens would get me to a -6? 3. So that leaves me with Al2O3. Okay, does this kind of make sense a little bit? Why we had to go to 6? Okay, when we're looking at an ionic compound, these numbers should be reduced. Okay, so if I had gone too far and I had said Al4O6, right, that would have been the same ratio, but these two numbers can be reduced by a 2, right? So when we're looking at ionic compounds, we need to make sure we have the most reduced versions of our formulas.
Why is that? Oh.
I was just talking through if it was bigger. If I had gone too far, if I had done 4 aluminums and 6 oxygens, that would have balanced my charges, but it would have been too big. So I need to have a reduced version. Okay, now I'm going to show you a little shortcut here. And you're going to be mad I didn't show it to you earlier, but that's how it goes. Okay? This is how we can combine our atoms a little bit quicker. Okay, but I want you to know the math behind it. I want you to understand the charge balancing behind it, not just the shortcut. Okay? So again, if I start with Al plus 3 and O minus 2. The way I can make this a little bit quicker is to do this. Okay, I'm going to ignore my charge for a second, ignore the plus or the minus for a second, and I'm going to cross down these charges, and they're going to become my subscripts. Al2O3. It always works like that. No matter what the charge is. Yep. Okay, I want you to know how it works first before I show you the shorter way to do it. Okay? Then you should still check your charges to make sure that everything's working like it should, but your cross-down method will work every time. Okay? But I'm going to show you kind of there's some like kind of little stipulations with that method. Okay? So let's try looking at beryllium and sulfide. Okay, beryllium and sulfide. So you can use whatever method works better for you. If it's easier for you to look at the charges and balance based on the charges, go for it. If it's easier for you to cross down those charges, go for it. Okay, but it's Be plus 2, S minus 2. If you use the cross down method, that would leave you with Be2, S2, right? Would you agree? But is that the most reduced version of this compound? No, right? These are both 2's, which means we can reduce them each to what? BES. That's where the cross-down method can be troublesome. Okay, you have to reduce that compound back to its normal form or its lowest form. So if you were just doing the charges, if you're just looking at the charges, you would have easily just said BES, right? Because it's a plus 2 and a minus 2. So you just have to kind of be careful, and you can use a mixture of the two methods, right? If crossing down works better for some and the charges works better for some others, that's fine. Okay? Do you understand how our compounds go together now? Okay, so now let's look at naming them. Naming them is super easy. The cation gets to keep its name. The anion ends in IDE. So the name for this compound is beryllium sulfide. That's it. Okay, so everyone we've been naming so far, potassium and phosphide, right? Magnesium and oxide, you just drop the and, right? Magnesium oxide is MgO. Potassium phosphide is K3P. Okay, so all you're doing is keeping the cation's name, and the anion gets the IDE. No, it's 2 words. 2 words. Beryllium sulfide. Okay. How are we feeling? Good? Okay, let's keep trying some. Yeah, Natalie. So now I'm going to give you the chemical formula, and you're going to give me the name. That's it. So I'm going to give you the balance formula. I'm going to do most of the work for you, and you're going to give me the name. Okay? Okay, so there's 3 there. I did the work for you and I balanced it for you. So now you're going to give me the written name. Where's SE at?
Selenide?
Yep. Zirconium selenide. Agreed? Okay, perfect. And last but not least, what is it? Mallory, what do you think? Silver nitride. Perfect. Perfect. Okay, very, very good. In the ionic formula, the subscripts itself don't change the name. Okay, so you've already done the work. I already did the work here to balance the formulas. So in these types of compounds, the subscript itself doesn't make a difference. We will study a type of compound that the number of atoms does affect the name, but these are not those kind. Okay? So for right now, when you're naming ionic compounds is very simple to go from compound to written name because it's just writing what you see, right? Silver, then nitride. That's it. Okay, now you're going to go from the written name to the chemical formula, okay, which is pretty much what we've been doing. Rubidium arsenide. If it's a 1 here, we just leave it off. Okay, so just Rb3As. Would we agree with that? Rubidium is a +1. Arsenic or arsenide is a -3, so we need 3 of those rubidiums to help us balance. Okay, zinc oxide. Grant, what'd you have? ZN2O2. Good. The ratio's right, but what's the thing that needs to be fixed? That's right. We need to go ahead and reduce that down. So your final answer should be ZNO. Okay. Okay. Last one. Maddie, what'd you have? SCCl3. Perfect.
Wait, so if that was supposed to be like the second one as an example, would it be like 4 and 4, would that still be like ZNO?
That's right. Okay. We're always going to reduce it down as much as we can.